So we have done this case when J by 2m form of the theta. We are doing this phase estimation problem. Problem algorithm, whatever. And so there was a unitary U and an eigenvector of it. This was notation, right? Yes, and this thing, and we were trying to find this theta, and we have done the case when theta is of the form J over 2m, in which case we use an m qubit auxiliary system, and then you can find this exactly with probability 1 actually. But this is of course a special case. What do you do when it's not necessary? This is what we will try to do now. So irrespective of whether theta is J over 2m or not, we have seen that this stage 3 state which was this thing, right? So there was this M, each of them had a Hadamard. There was a 0 tensor M that was put in. There was an n qubit psi. This thing is happening in C2 tensor n. This the unitary operator is an operator on this, and the vector is a vector of this. And then there was this controlled unitary, and this is the stage 3. This thing is anyway dumped, and this goes through the quantum Fourier transform dagger. Yes. This is the psi 3. So the state of the circuit at stage 3 is given by This was without any assumption of the theta, yes? We discard the last n qubits. Discard this part. So we have this. After the discarding, we apply the 2 power m dimensional quantum Fourier transform dagger to the first m qubits. So remembering that this acting on J is 2 power m by 2, yes, with this minus sign there. To get, you apply this thing here, it's of course linear, it goes all the way up to here, and then this is the thing. So you get 2 power minus m, these two, and this thing remains. This thing remains, it reaches here. Call it K prime. The J is the K here, yes? So it's the K, and the K has become the K prime. And then there is a by 2 power m. The running index now is K prime. Yes? And that is equal to bringing the K prime outside, yes? We'll do that. Yes. And there, with the minus sign. Is this okay? This is the state here at this point. Call it size 4. If we assume theta to be of the form j by 2 power m, this is just a single element, but here you have all these elements. Fine. Make a measurement here on these in this computational basis. So the basis which you would call the sigma z tensor n eigenbasis, yes? Whose one of the eigenvectors is these zeros. So, I mean, it could still be hard to do it, but it's sort of as simple as it could get, that you make measurements on each of these lines independently, yes? There's no joint measurements required. Yes? So you are making a measurement, suppose you want to make a measurement in this basis. So this basis is like that, yes? This basis, this computational basis is like that. But this is making a measurement in this basis in this part and in this basis in this part. So we keep the Stern Garla in the z direction in both, which can be difficult in some situations, specifically doing so many of them, there will be errors and so on. But it's at least a basis which is the basis in which you created your initial state. So there are no hidden unitaries there, the local ones, and more importantly perhaps is that there are no entangled measurements. It's not a measurement in the 0, 0, plus minus 1, 1, 0, 1, plus minus 1, 0, this type of basis. This, well, mathematically these two bases are the same. They don't have any same meaning, they have the same status. But experimentalists will tell you that this is much more difficult. So for example, you can show that if these are photonic systems, and if you are using only linear optics setup, then there is a paper long ago, in 1909 or something, that you will not be able to make a measurement in this basis, using only linear optics elements. So phase shifters, homodyne detectors. So this is what I'm saying, that we have a situation that is as simple as it could get, while still being, of course you know that quantum computers are difficult to build, nobody has built it as yet, the big ones, so it's still difficult. But what I'm saying is at least that measurement part is, it cannot get simpler. And so we make that measurement, and the probability that the result is some j going from this is, call it pj, and it's this squared, yes? Square, modulo square of this. Yes?
We are projecting J.
You're projecting onto j. So
Just get the number.
pardon? You're just replacing the k prime. I'm calling the running index j instead, because just, you can call it k prime as well. I just want to connect with the previous notation. The previous notation was j over 2n. So here, so in the previous case, this was 0 for a given some j.
The previous case, the k prime was an integer that we divided by 2 power m. That was the thing that we were trying to find.
Exactly. It's the same thing here.
But if it's
K prime is an
any
integer.
theta, how is that, if it's any random theta,
Yes.
how is that we are resolving at that we can project that number in this 2 power n minus 1 binary digit? I don't understand how is that.
That is not possible.
Then what do you mean when we are getting a k prime, a certain integer out of it?
That is not an approximation to theta.
We are getting all the integers of some unknown.
So the theta, so in the, so there are these two cases, yes? So we have done a special case. In the other special case, first of all, in both the cases, the special case and this general case, the u is given, the psi is given, the theta is not given. But in that special case, the theta was promised to be an integer divided by 2 power n. And then we looked at that m and chose an m qubit auxiliary system. And it worked, it was only one thing that will click, nothing else will click. And the one that clicks, you find out that j, and that is, that divided by 2 power n is the answer. In this case, we haven't assumed that. But we can still make a measurement in the j, the same basis as before. This is, that's this, I mean, you can remove this k prime, call it, it's the same thing. This was the state the last time, except that this was 1 for one j and 0 for the rest. The state that came out was a Fourier rotated j. So when you take the inverse Fourier transform, you got the j's. So make a measurement, you get one of the j's. Here that has not happened. But we could still make a measurement in that same basis. Because now we are not told what is given. So but we still want to follow that same technique and see what happens. Now that same probability, an arbitrary j is this, for an arbitrary j. And for an arbitrary theta, the theta is still we don't know. So there is some algebra now which I will not do. You can, and anyway, this algebra depends on a on sort of an inequality, mathematical inequality that is very difficult to prove. Took me several pages.
The earlier case we considered was like a special case of this one.
Is a special case of this one. Yeah. Where we assume the theta is of the form J over 2n.
So in this case, like the maximum probability would correspond to that special case.
This is what we will do.
it's
So
like-
we will, so they have given a way to give a bound on this number. I will write that bound. To find that analytically will require some algebra. I will not do that. But the point is that this Pj in the last case, if you find out all the Pj's, it will be 1 at one place and 0 everywhere else. This time it will not be like that. But it will still be a hump. And you choose that topmost point as the j which corresponds to the theta. And you take that j, divide that by 2m, 2 power m, and call that as the theta. And this gives you m bits of precision.
So this experiment you cannot do once and decide the theta. Can you?
Yeah, you will do this experiment only once. You have this psi, come here, and whatever clicks, you mean, this one, no, the previous one, yes, sorry. Yes. You have to know the probability. You have to know this profile. Yeah, that's. So, the good thing here is, although that is still experimentally daunting, is that the thing that we threw out was exactly in the state psi. The psi was never altered. So, to find these probabilities, you have to run the experiment many times. You could, in principle, use this psi again back into the channel. But then, of course, this is experimentally daunting.
So would this be anyway advantageous to the classical?
Yeah, so this comes later. Yeah, we have not. So this we are looking at a very abstract way. We haven't yet said why all this we are doing. We will do that. So we will say why we are doing it. Currently, it's very abstract. We have, someone has given us a unitary operator and an eigenvector of that. It's promised that this is an eigenvector. We have to find the phase of it, the eigenvalue of it. Why would one be interested in doing that? It's because it's related to Schor algorithm. You will see that.
Because this boils down to like figuring out the hump, where the hump would be.
Exactly. So the point is just this, that you plot the thing as j, and it looks like this, and you choose this j, you find out that whatever that j is, divide that by 2 power m, and you claim that this is the theta. And you get that correct to m bits of precision. And now in this case, the m is not given to us, so you can choose your m. Yes. And the choice means that here you have to choose more auxiliary system, and this will become harder, and this will become harder. So as you increase your precision, of course, it becomes harder and harder to do the experiment. Which is intuitively satisfactory, of course. Not experimentally satisfactory, but intuitively this is what. So, but the point that I want to make here is that this maximum of these probabilities you can show is independent of n is greater or equal to 0.4. So this is the, so to get from here to here requires a lot of etc. If, I mean, for example, in this is given in this theta book. There's no quantum mechanics there, and it's just a lot of algebra. So this, I mean, often you must think that this is sort of a low number, but it is not a low number. You see that this is independent of the m, yes? So it says that you have this theta and you want to know it up to m bits of precision, and this 0.4 is the probability that every bit of those m bits is correct. Yeah. So this is actually quite a high probability. There are two more things that we will not go in that direction. We want to go to the Shor algorithm quickly. But there are two things that one has to remember that we are skipping. Number one is this QFT dagger 2M easy to implement? Now this easy is not in the experimental sense, it's in the sense of complexity theory, that because we will finally be using it for the Shor algorithm, which wants to bring down an exponential into a polynomial, well, a non-polynomial into a polynomial, we have to be careful that there is no non-polynomial hidden here. And for this, you can show that this can be implemented with n square gates. So there is a polynomial here. And not a non-polynomial, super polynomial. And number two is this one. Is this, what was the name? Is lambda mu, no? This is the same question.
N
This-
square, you mean n is 2 to the power m?
M. M. This is the m qubits. And you can implement the quantum Fourier transform and n qubit quantum Fourier transform with n square gates. Similar to qubit gates. This one doesn't have a general answer. For a general in the sense doesn't have a general answer for arbitrary u, and it could actually be negative for an arbitrary u. It may not be implementable for an arbitrary u efficiently. Efficiently means with a polynomial of n this time. Sorry, polynomial of m plus n. But for the unitaries that we will use only specific types of u's, and for those cases it will be efficient in polynomial in n plus n. But again, this we will skip.
Why are we demanding a polynomial in m? We should be worried about a polynomial in 2 to the power m, right? Because that is the number of precision bits here. Not bits, but that is the exact precision of the phase.
No, it's the number of qubits that matters, because that's what stores the information. So we will finally have numbers, and we will take them into bits, and those bits will be my inputs to the system. That is how complexity theory is counted. I mean, in classical complexity theory, you count the number of bits, and you see whether your something to do it like factorization, whether it is polynomial or exponential in the bits. That's the way to count. You can count in 2 power n, that's not a problem. But then 2 power m hides exponential within it. Okay. We will now require some algebra, some notations from algebra. So, probably many of you already know, but this is from group theory and finite groups. This is Z, but this is the notation that they use. We will need this notation, so we will define what is the meaning of this phrase. First of all, if these three are integers with n greater than 1, then this thing, if I write A is equivalent to B mod n, this means n divides m. That is this equivalence classes. Notation. This Zn, for our purposes, is 0 up to n minus 1, a set of integers. Okay. There's some more structure allotted to it, but let it just be this. So you start from 0, go to n minus 1, n is an integer, of course.
So what is the star then? Let it start.
Come. Zn star is the set of all the elements of Zn such that the greatest common divisor of A and n is 1. That is, Zn star is formed by all the elements of Zn that are co-prime with n. Yes. Doesn't have a common factor. Just some notations. These are standard notations from finite groups.
A and B are given to specific.
We will come to that later, yeah. Yes, A and B will have a picture, but in this Zn star, A and B doesn't have, A is anything. This A is, doesn't have to be that A. And call it C. We will be interested in the number of elements in this Zn for a given n. Call it phi n, cardinality of Zn star. But we are not the first ones to be interested in this. There are big people who are interested in this. It's called the Euler's phi function. It's probably the nth thing named after Euler.
Literally the nth thing.
Pardon?
Literally the nth thing.
No, it is said that Euler has done so many things in so many places that in mathematics they usually don't call things after Euler. Still there are some exceptions, but most of the time they call some function, if Euler has done it, they just ignore it. They take the second person. We need some structure for this Zn star. We will associate the operation multiplication modulo n. With this operation, it forms a group. Let me check. In particular, for a given A belonging to Zn star, some element of this, So some number that is co-prime with the n. There exists a unique B belonging to Zn star such that AB is equivalent to 1 modulo.
SP is that. No.
This is just an example. I mean, call it something else. Call it priming. This is a general notation. This is a running index. Fine, this is the property of a group, yes? We will, and it's just, this is just some notation. So we will write this as B is A inverse modulo. It would mean this. Which would mean this. So we have sorted out with this. This we had sorted out in school. Now we come here. Okay. The order of a given element A belonging to Zn star, or this phrase is also sometimes written as the order of A modulo n. Is the smallest r such that A power r is equivalent to 1. Of course, all multiplications are modulo n. Well, you can ask, what is the guarantee that such an R will exist?
So do
What is the guarantee
that is the operation. There is a group. Does being a group satisfy this?
Not necessarily.
What?
Why will it satisfy all the time? Does it?
A finite group always has an order.
Yeah.
It has same logic.
Yeah, exactly. Yeah, because it's a finite group, that's the reason. Otherwise it doesn't.
Fine. We put n minus 1 already, so it's a finite group.
Exactly. So what you know is that this A power phi n is always equal to 1. So if you take the Euler phi function on top of anything, it always gives you 1. So the number of r's that satisfy this is a non-empty set. So you can find the minimum of that. So this thing holds for any integers a and n, provided n is greater than 2, with the GCD between a and n to be equal to 1. And in this case, a and n are co-prime, we know. So this thing is satisfied. This is called another Euler theorem. Fine, why did we do all this? We did all this because we will do something now called the order finding problem. So let me give you the statement of the problem. In the problem, your input is a positive integer n, moreover it's actually greater than 2. We have an integer greater or equal to 2 and an element A belonging to Zn star and the output is the order of A in Zn star. This is what we were doing until now. So this is the order finding problem. In the input we will give an integer, any integer, 2 or above, and an element A of Zn star. So an element A that is co-prime with n. And then we are supposed to find the order of A, that is we are supposed to find the smallest r that you take the power of that, but whenever you multiply modulo n, and it should give you the 1 identity. Classically, meaning if you try to do this problem with classical algorithms, we haven't defined what is hard and easy. There is a complexity sense, we will not go in that direction. Roughly means it's not a polynomial, higher than a polynomial, higher than all polynomials with respect to the input, the number of bits in that input.
Well, the numbers are very, very big, that's why.
How is this exactly related to the factorization problem?
This is related to factorization, but that comes later. First, we will show that this problem can be solved efficiently by using the phase estimation.
So does hard mean like exponential?
It's not exponential really. So it's super polynomial but sub-exponential.
So exponential powers or logarithms, something.
Forgot the exact thing. It's not exponential, but it's higher than all polynomials. And it has never been proven. It's all the existing algorithms are like that. Nobody has proven that there is no algorithm that is polynomial in the classical case. It is widely believed to be true. So, we will try to do this by using by using a quantum machine, a quantum device, and exactly the thing that we will use is the phase estimation algorithm. Solving the order finding, which is this problem that we just stated. This is what we want to go now. So, assume that sum n greater than 2 is given. So, we want to take it into bits. Let n be the number of bits needed to encode the elements of Zn star and Zn in general in binary. So that it's like this actually. Well, it's log n, but to be more precise, it's the floor of this number plus 1, roughly log 2n. But we will take this n and given any A belonging to Zn star, we define an n-qubit transformation call it MA, A is the suffix. As on the X, where X belongs to Zn, this is there is a gap in this definition, but it's sort of more of a pedagogic thing, is that this is the n qubits, which is 2 power n, and there's a gap between 2 power n and n. N is, capital N is smaller. In general. So you can take the rest of them to identity. For example, you can take whatever you like, it has to be unitary at the end. This is the only constraint.
But we are defining this MA only for A belonging to Zn star.
Yeah.
But we are
A is
applying it
Zn.
on a matrix of Zn, on a vector belonging to Zn.
Exactly. So
It's
we have
not even a
defined
Zn.
an n qubit transformation. This n, this 2 power n is sort of n, except for a small error.
It's an n cross n matrix. Small
This-
n cross capital N.
This one,
No, MA.
this is n cross n. I want it to be n cross, is the n cross n matrix, but n is not available in nature. In nature, what is available? Well, in principle it is available, but in practice, when you try to do the experiment, we usually do it with qubits. So what we have is 2n by 2n matrix. So what I want to say is that here we have defined only this one. And the remaining part you take it to be an identity. For example, you can take anything else because that will never appear in your experiment. So first of all, but this is just transformation. We have to first of all see whether this is a valid physical operation. So you can show, take it as a problem. MA is unitary. Show the unitary. This will be our U of the phase estimation problem. We will apply phase estimation to this operator. And what is the vector? Come to that. remember that there were these two gaps that we left. One was whether the inverse of the quantum Fourier transform m qubit can be implemented. The other was the lambda mu, whether it can be implemented. So here it's that we need to show whether this can be efficiently implemented. We will not go into that, but I want to claim that this can be implemented efficiently. So again, this is a meaning. It actually is order of m into n square, 1 and 2 qubit gates. So we have not been able to answer it for an arbitrary u, but we will be using it only for this u, and for this can be done. I am still not doing it, but this can be done. So it doesn't hide anything, any exponential, because that is something that we will need later. Come to another problem. Show that this call something as psi j. What is the psi j? It is 1 over root r. This r is the order of A. On A plus omega r to the power of minus twice j a square. So when I write a square, all multiplications are modulo n, okay? So this a square means a into a modulo n plus omega r this is what you have to show. This you already guessed is this. You can just explicitly use this and show this. It actually looks like this. So first of all, operations in this a power some n or p are modulo n. R is the order of A in Zn star. And J runs from okay. We have said that we will subject this thing to phase estimation, but that means somebody will give us an eigenvector of MA and we will be estimating its phase. Which eigenvector are we given? These are the eigenvectors. Well, this is a very suspicious statement, okay? We want to find we are given the N and the A, so we can build the MA. Can be experimentally troubling, in principle we can. We can implement the lambda M MA, again it can be experimentally problematic, but at least we in principle know that this with Mn square gates we can implement it. But this psi 1 contains information about the R. And that R is the thing that we are supposed to find. How are we going to get hold of the psi 1? So, it's of course not something that you should believe, but let us believe for a while and then we will see what happens.
Sir, in the classical algorithm, we were saying that we don't yet have a polynomial algorithm. Polynomial in n or phi n or what?
Polynomial in the number of bits that are contained in capital N.
So log n. And this we are trying to show that in small n we can find a polynomial.
So, okay, so well, not R factorial, huh? So ignore this for the moment, okay? We will remove this trouble soon. Maybe tomorrow. And but ignoring this problem, we now subject MA to phase estimation for the unit design. Okay. Fine. So what do we want to implement? We want to, so once more 3 is M, okay, and 4 is N. All these are hollow marks. Put in a psi 1 here. The lambda m MA the inverse Fourier transform and the measurement in the computational basis. This is done. Yes, we'll do this. Now, so from there, put J equals 1 there. So we know this, so now we use phase estimation to find this theta, which is the 1 over R, and hence R with significant precision by choosing suitably. Well, this of course hides a lot of algebra and etc. This M has to be chosen. This is in our hand. This is this is beyond us, but this is in our hand. We can try to increase it to get better precision. But of course, that better precision comes at the expense of having bigger lambda MA to be implemented and bigger QFT to be implemented. But it's the same thing as before. So we still have the problem of Simon. So the point is that it is not possible to get hold of psi. We will do something else. But we will still use this algebra. First of all, note that if you take this summation, remember the psi case, these were eigenvectors of MA. Will give you 1. Well, show this, huh? Now we have this information that running the phase estimation procedure on psi k, if I use psi k here, the state of the entire system m plus n just before measurement and dumping, so the measurement here and a dumping here, so at this stage the psi 4 but with the thing that we dumped is some phi k, because the thing that comes here depends on this, yes? But this thing doesn't change. Yes? says for this. This is the new notation. This is the thing. Whatever comes out here before the measurement, if the input here is psi q. So we know that the auxiliary, not the auxiliary, it's the system. I mean, it depends on what you call the auxiliary and the system. The last 10 qubits is in psi k which is the same as the input. Yes, whatever was the input here, it came out the same. We are not dumping it. So now, running the phase estimation on 1. Remember the 1? 1 was the sum of all the eigenvectors. So, this is the new phrase we are using. Running the phase estimation on 1 doesn't have a meaning. 1 is not an eigenvector. But running the phase estimation on 1, I mean that I put the input here as 1. I will not be finding any phase or anything because I mean there is no phase in the first place anyway. It's not an eigenvector. But since I have the preparation, I have the machine there, in this bottom n qubits, I can put 1 inside, which is actually sum of all these cycles. I can put it in. I am not trying to find any phase anymore. But it's a quantum machine, it gives me an output here. So this is what I mean by running the phase estimation of 1 is I put 1 there in the bottom n qubits. The state immediately before measurement and dumping is the state here on this line is yes. It will be a superposition of all the options. This is what we had, right? Sorry, where was the? So there was a mistake in the last page. It was on R minus 1. So this thing that was written here, 1 hope that is true. I think the R, the eigenvectors only ran up to R minus 1.
Even Psi-j, the power of omega was
Up to R minus 1. So,
It's the same. Omega to the power R is 1.
omega to the power is R is 1, that is true, but what we want is whether this is true. I am guessing that this is true. I have to do the calculation once more. I have written it wrong here, but I think this is true. Okay? So assuming this to be true, so instead of, if I had put psi k here, we would get psi k here, which is true for all the k's. And now I put in 1 here, which is superposition of all of them. And here I get different things. Those different things have come here. But this thing has come out the same all the time. Except now, this is no more a product here. It's an entangled state that has come out. I mean, most of the time it will be entangled, except in some strange case. Fine. Just, you have some class now? Just 2 more minutes. Well, this. Or maybe we stop here. Quite a few. But tell me if you have any problems here. So once more, we have the problem that we have in our hand is to find the order of some A that is co-prime with a given n. Yeah, so n is some number, and I want to find the order of another number A that is co-prime with n. Yeah, this is our problem. And then we have built this apparatus, we have built this unitary that depends on that A and n. And we have built this this machine. In that machine, we know that if we put in these eigenvectors of the of this MA, then we will get out the eigenvector of the same eigenvector here, and we will be able to estimate the corresponding phase. But the trouble is that none of these psi k's are known because all of them contain that R, which we want to know. But now we have realized that if we add up all these, this gives you some vector that is independent of the R. And so now what we are doing, we are using that same machine, and here we are putting in that vector 1. That vector 1 is not anymore an eigenvector of MA, so we are not after finding any phase. What we are after, we will do that next.
How do we physically implement arbitrary unitaries in the sense that if I want to implement a certain unitary of my own choice on some state, on a system, how do I create that?
Yes, so this is in general a difficult problem. You have to do it case by case.
Yes, so how do I make MA? Like I would think that
Yeah,
I would
so
have to find a corresponding Hamiltonian or
it essentially depends on the actual implementation. What they have shown is that you can implement this in principle using a polynomial number of single and multiple gates. But in actual practice, it could be something. Which one, because there is not a unique decomposition. Which one is good and all. This depends on the exact physical substrate that you are using.
So that one which is the sum of all Psi-j's, that one is just the 2 qubit one tensor n, is it?
Pardon?
I mean, the one which we have in Psi J. Psi J is
One is the number one. It's
one,
because you remember that we had this capital N, and from there we built the Zn, which is just the 0 up to capital N, and corresponding to that we built a 2 power small n qubit dimensional system. In that there is some vector that is called 1. You will have all of them, 1, 2, 3, 5 up to n, right? Capital N. And of them there is someone called n, someone called 1, and that one is this one.
so if it is difficult to get hold of say Psi 1, then and since 1 is the superposition of all Psis, then how are we constructing 1?
No.
First bit
One
of
The
one.
point is that you know on paper that this is a superposition of all of them,
Okay.
but this one doesn't contain any information about the R. So in practice it can still be difficult, but I mean in principle you can get the one. It does not need. You can in principle build the one. You can input the one, and it does not have any information about the R.